Welcome to Gravitational Potential. You are already familiar with the concept of gravitational potential energy, which is mass times gravity times by height. Gravitational potential is the energy per unit mass. So V, or gravitational potential, is equal to the gravitational potential energy per unit mass, which is equal to the gravitational field strength multiplied by the height. And we tend to think of it being a change in gravitational potential, and that would be a change in height, or even a change in radius, because when we're dealing with gravitational fields, we tend to be looking at the distance away from the center of the mass, which we call the radius. Another way of approaching this would be to consider Newton's law. To rearrange to make work done, or force times by distance, and distance here would be the radius. And then we have the energy, the work done, per unit mass, leaving us with Gm over R. In this diagram here, we can see how gravitational fields are depicted. This is a graph of gravitational potential. And here, that's the zero line. Gravitational potential has a value of 0 at that position. And that value only exists at a distance of r equals infinity away from the center of the masses. You can see that the trend of this curve is eventually to reach the 0 line, but that only happens at infinity. Any object that is in close proximity to these masses is going to be inside this gravitational well. And if it's at this location, or whether it's at this location, it's going to have a negative value of gravitational potential. If we want to raise the object to a higher level, further away from the mass, then we have to put energy in, but it still ends up with a negative value of gravitational potential. If an object is moving closer to the mass, then what's happening is that it starts off with a small negative value and ends up with a larger negative value. It's the same as if you had an object and you wanted to raise it higher up a hill. You would have to put energy in, and that energy gets turned into gravitational potential energy. All we're doing in this situation is we're saying how much energy per unit mass. If the object is rolling down the hill, then it loses gravitational potential energy, and the energy forms something else. And you could potentially get energy out of this system. This is how water mills work, for example. Water flowing downhill turns a wheel, and that energy is used to grind grain. So when we think about gravitational potential, this is always going to be a negative, and we tend to think of it as a change, and that change is usually due to a change of radius. We can graph gravitational potential. Because the largest number it's ever going to have is 0, we can put the 0 line high up here, and we can see how it changes with regards to radius. An object can never be closer to the center of the mass than it is on the surface. So let's think about the smallest radius being the surface of the planet, so the radius of the planet. And at the surface, it's going to have the lowest value of gravitational potential. So this would be on the surface. As the radius gets larger, the gravitational potential will increase. And we can see from this relationship that gravitational potential is proportional to the inverse of radius. So this is going to be a curve that never quite reaches the x-axis. The gradient of the line is going to be the rise divided by the run. The rise is the change in gravitational potential, and the run is the change in radius. That's this relationship over here, which is equal to the gravitational field strength. We know that gravitational field strength is F over m, which is here in this formula, or we can get it from Newton's law. The change in gravitational potential is equal to this, which is also here. Therefore, gravitational field strength is equal to gravitational potential divided by radius. And we can see from this relationship here that gravitational potential is proportional to 1 over r squared. If we put this in a graph, as the radius increases, the gravitational field strength will decrease, and it will decrease according to the inverse square law. Again, the smallest radius that can exist is the radius of the planet itself, and on the surface of the planet, we're going to have the gravitational field strength on the surface of the planet. So the graph will start up here, and then it will follow an inverse square law pattern, never quite reaching 0. If we have a look at this relationship, we can see that if you take the area beneath the graph, that would be gravitational field strength multiplied by radius, and that would give you the gravitational potential. So this area under here is the gravitational potential that it would take to go from this radius to this radius. Those of you who are doing A-level maths might be tempted to use an integration to solve for problems like this. However, A-level maths is not required for studying A-level physics, and therefore the techniques that you're going to be assessed on in your examinations will require you to use non-A-level maths techniques. So I recommend you use techniques such as counting the squares.